So good evening, good afternoon, everyone. I hope we are all fine. So welcome to today's talk. And before we proceed to our talk for this month, I want to first of all make an announcement concerning our upcoming event, AMRS 2026. But before I make an announcement, I wish to confirm or to check whether we have any of our members from AMRS board here with us. Do you have any, maybe to say hi to the members before we start? Someone from your end, can you see?
Yeah, I think they're still on their way.
Okay, thank you.
Yeah, I think they're still on their way.
Great. So I will make an announcement on the upcoming event. Then I'll request Samuel to introduce our speaker for today. Then we shall proceed. So December 2026, we shall be hosting our 13th International Conference of the African Material Research Society. That is the AMRS 2026 here in Nairobi, Kenya, which shall start with a pre-conference on 5th to 6th December. And I'm happy to announce that our speaker for today, that is Professor Natalie Stingelin, has accepted our request to offer a workshop in the pre-conference. So I look forward to seeing most of us register for the conference. So the theme of this conference will be material science and innovation, driving sustainable development and socioeconomic transformation in Africa. And we shall cover quite a number of themes, as you can see what we have here, including AI in material science. And of importance again, we shall have various special sessions during the event that will include a session or a symposium on AMRS, EMRS, and we also have the African light source, and we are also looking for many others, which we shall announce as we proceed. So with that, I want to welcome you to AMRS 2026. And I want to take this moment to welcome Samuel to say a word and then introduce our speaker. Thank you.
Thank you very much, Victor. My name is Samuel Chigome. I'm based in Botswana at the headquarters of the African Materials Research Society. So the main objective of the African MRS is to promote excellence in all aspects of materials research. So basically serve as a platform for promoting collaboration, looking at all the 54 African countries, and then also connecting Africa to the rest of the world. I'm also happy to announce that in addition to being the headquarters, from 2021, we became the first ever regional office in Africa of the International Union of Material Research Societies. So what it means now is that our responsibility for promoting materials research has gone beyond just primarily focus on Africa, but now we connect aggressively with the rest of the world. So and that has helped us to be able to facilitate, I think, the connections of African researchers in the rest of the world. So with that, I would like to first of all thank our guest speaker for today, Professor Natalie. Thank you very much for agreeing to give a talk. It's interesting that we met at a it was Polymer Science Conference in Mauritius earlier this year. So I think that's the power of connecting. Because when you connect, you establish relationships, and then it leads to so many other things that will come through from there. So I think that's what we try to do as African MRS, connect people. So in terms of introducing Professor Natalie, let me just, there's someone who's making, sorry, there's okay, it's gone out quiet. So Professor Natalie Stingelin is the chair of the School of Material Science and Engineering at the Georgia Institute of Technology. I think normally call it Georgia Tech. So I think before moving to the US, she spent quite a bit of time in Europe, in different countries. I won't specify them one by one, but all I can say that they're all prestigious institutes where she worked in the UK, Switzerland, Netherlands. And I think as a result of her outstanding work, she was recognized, I think, by a number of organizations. So she's a fellow of the African Physical Society. She's also a fellow of the European Academy of Sciences. She's also a fellow of the US National Academy of Inventors. So among other organizations where she's been recognized. So I think this shows that indeed she's done some outstanding work with that recognition. So I think what I can say about a research area is that broadly it covers functional polymer materials, polymer physics, organic electronics, photonics, and bioelectronics. And for today's talk, she's going to be talking about cool plastics. That's the title of a talk. So I think with those few words, Natalie, my assumption is that after we shared your profile with uh, all the people in Africa, they must have gone through to see what your work is all about, and everyone is very much looking forward to what you are going to share today. So, with those few words, the floor is yours. Please go ahead. Thank you very much.
Thank you very much. Thanks actually for being here. And I apologize for the background noise. That was me because I'm in Sweden in a hotel. And exactly now some people came in. But yeah, ignore the background noise. I'm really happy to and delighted to give this webinar at Thanksgiving Day in the US. It's a great opportunity, and as Samuel said, one nicest part of being a scientist is to be connected and get connected with people across the world. And today I show a bit of hobby project that started possibly 20 years ago in my group. For those who know me, I'm a trained polymer scientist. I worked with semiconductors, but more and more I thought, well, can we do more with plastics? And this is really about can we actually turn around the reputation of plastics that they're bad? Because whenever you go somewhere and you say you're a scientist, you work on polymers, you work on plastics, people say, well, they pollute. But hopefully today I can show you that they can do many good things as well. And in particular, I will show how they can be used to manage light and heat for buildings, etc. And before I start, I just want to thank the people who really did the work, students here at Georgia Tech, but also students like Stefan and Kevin at Imperial College, where I was for 11 years, as well as collaborators across the globe. But since this in particular also is for students, I thought I first talk quite briefly about myself. So I'm originally from Switzerland. So this small little country here in the middle of Europe. And if you zoom in, I come from the southeast, yeah?
Sorry, Natalie. Sorry.
Yeah.
Yeah, it looks like on my side they are not showing the slides. I'm not sure if
Oh,
I'm not sure if it's everyone else or just me.
let me see. Yeah. Okay. I think I pressed share, but it didn't go through. So hopefully now
Oh,
it's
okay.
there.
It's showing. Okay, now it's okay. Yeah, you can just go to presentation mode.
Okay, thanks for voilà. So let's start again.
Okay, all right, thanks.
Well, I really want to talk about plastics and the greener world and light and heat management. And as mentioned, there was a big crowd of people, both at Georgia Tech, at Imperial College, and I have to get the pointer back, that contributed to this work. Though, as mentioned, I want to first actually just show students what happens when you do science. I really come from this very small country here in Europe, Switzerland. And within Switzerland, I'm from the southeast, so close to Austria, Liechtenstein, Italy. And my area is a bit special because I come from the city that is Swiss German speaking. But already when you go up here, people speak Romanish. And actually in these type of valleys over here, they speak Italian. And just to give you an idea how it looks, so it's in the mountains. We do grow some wine, but maybe more people will know the area from the story of Heidi or actually the World Economic Forum in Davos. So they're all very, very close by. Then I went to Zurich to study. As Samuel already said, I have a PhD in material science from ETH. Went then to Cambridge, Philips, completely different scenery, where I worked in industry, but I somehow, after a few years, I really didn't like industry. So I moved to London in 2005 to become an assistant professor, first in the East End, at Queen Mary University of London, then at Imperial College London. In 2016, I moved to Georgia Tech. And since we talk about Georgia Tech, I was attracted by Georgia Tech. It's number 4 of the graduate engineering program in the nation, so in the US. And if you look at public universities, so we are a state university, we are on number 2, actually. And also in the undergrad engineering rankings, we do very well. We're number 3 nowadays. And as mentioned, I'm a material scientist. So in the undergrad program, we are now in 2 consecutive years, number 3. And on the graduate program, we are number 7. So that's just a bit an overview and hopefully also to show one never knows. I wanted to become a marine biologist and my parents said, well, what do you do as marine biology? Just in Switzerland because we don't have an ocean. But then, well, I ended up in the US anyway. So one can plan, but one always have to make sure not to close doors and take the opportunities and move around and just learn and do science. So that brings me back to light management. How and why do we need light management? A good example is really for buildings. So when you look just at the US alone, 40% of electricity use and 30% of the carbon emissions come because of residential or commercial buildings. And in case we could regulate light and heat much better, we could reduce energy consumption by at least 10 to 20%. But light management and heat management is also needed for like devices like solar cells. So while you want to catch light, you also don't want the solar cell to heat up. And this sort of schematically shown. In addition, we have a lot of parasitic like reflections in solar cells that reduces the amount of light that gets into the structure and therefore the efficiency of the solar cell goes down. And clearly, if you think of solar cells, if you're in Saudi Arabia where you have a lot of photons, that's okay. In Atlanta, possibly fine too. But in London, where I lived a long time, or also here in Sweden, well, if you want to use solar cells, you really have to attract every single photon into the device that you can. And for those who don't know about solar cells, it's a very simple structure. So at least for emerging solar cells like metal halide perovskites or polymer solar cells, you have 2 electrodes, the anode and the cathode. You have an active layer in between. And the key is, as mentioned, you need a good photoconversion, meaning if you shine light, you create excitons, a whole electron pair, and those you want to convert into electricity. So the more you create those electricity from an exciton pair, the better. Clearly also, once you create charges, you have to get them out. So that's why a lot of the polymer solar cells, they're relatively thin compared to silicon ones, because in case they're too thick, the charges never reach the electrodes. And then you also need, of course, good light absorption. If you don't get light in, it's not absorbed or it's not captured, of course, you can't get a good photoconversion. And over the years, there has been really a lot of progress. So if you look at the efficiency, and the x-axis here is actually time, you see how efficiencies of all kinds of solar cells improved. Nowadays, we have the crystalline silicon solar cells over here, more modern, complex solar cells where we have efficiencies of 48. And then this class of polymers down here. So these are the emerging solar cells where we get nowadays to efficiencies of about 21, 22%. And this increase in these emerging solar cells was because of new materials, interlayers, and device engineering. You wonder, why do we even care about these solar cells when up here we have systems that have much higher efficiencies? One big reason all of those devices down here are semi-transparent. So they can be integrated in buildings and other things. But because they're semi-transparent, that tells you not all light is absorbed or harvested. So what can we do to help with light harvesting? And that means, as mentioned at the beginning, we have to manipulate light, and we have to manipulate light with polymers. The reason is these emerging solar cells are done out with very soft, often pretty sensitive materials. So inorganic light guiding structures cannot be used simply because of the fabrication methodologies that are used for those. And simple structures that can be used are often multi-layer structures. And multi-layer structures of low index and high index materials, you stack them up, and at every single interface shown here, you have constructive and deconstructive interferences, and that means some light will be reflected. And as you also see here, the more interlayers interfaces you have, the more light is reflected. Also, the way we design these structures, and I will get there, like the thickness of those layers matter to control what light is manipulated. So how can we use such structures? So one is really just to reduce reflection. So if you look at solar cells, you see that actually also current inorganic solar cell, 30% of the incident light is reflected from single crystalline silicon solar cells. So that's a big loss. We could actually get them much more efficient in case we could harvest this light. So we have here, just as an example, we have these glass tubes. And that shows really how big the reflection is on inorganic structures. So how can we solve this with photonics and with polymer photonics? The most simple one is really anti-reflection coatings. And this has been done. In many cases, they simply use fluorinated polymers. So PFP is a fluorinated polymer. Why? Fluorinated polymers, because of the fluorine, they have relatively low refractive index. So if you come from air, low refractive index, fluorinated polymer, bit higher refractive index, there's a gradual change to your silicon and not much light is reflected. However, as you know, fluorination is nowadays not that well perceived because fluorinated compounds can get into the environment and really be very destructive. So in case we do photonic structures, this changes. As proof of concept, we still use the fluorinated polymer, but also a polymeric material with titanium oxide hydrate species in there. The inorganic is needed to increase the refractive index. I get there. And if you just put 2 layers or actually 4 layers on top of these structures, key is you keep one thinner than the other, you see immediately the effect. If you have glass, the reflectance, then we do the 2 layers, 4 layers. You see we drastically reduce actually the reflectivity of this glass. And you see that here. This is the tube I showed you before and after coating. And once you coated it, you see the reflectance is drastically reduced. So actually the glass nearly looks black. The good news is here, because we actually use photonics, this red layer could also be done actually with um, non-fluorinated polymers such as PMMA or so. What else? So this is the structure I already showed you before, where we have multiple bilayers of a low and high refractive index. What is different to the anti-reflection coating I showed you just before, here both of the layers, the gray, the high refractive, and the light gray, the low refractive index material, they are of the same optical thickness. And optical thickness means the physical thickness, D, times the refractive index of that material. And if you want to reflect or use this structure to do something on light of the wavelengths lambda n, you have to have this thickness to be this optical thickness 1/4 of the wavelength. And if you now stack them up, as shown before, 1 layer, 2 layers, 3 layers, 4 layers, you see how light starts to be reflected in a specific area, so in this case, blue. And you can follow that. So these are experiments where you measure the transmittance. You see the more layers you have, one period means one low and a high refractive index layer. You start to build up what the physicists call a stop band. So you start to reflect the light of lambda divided by 4. And this is often used in nature. For instance, this butterfly in Australia that looks blue, they have these photonic structures on there. I also have to say, we use polymers and we do dip coating, so a very simple process. And what is really very interesting and intriguing is that when you make these layers, you get extremely good interfaces. And that's something that is very difficult to achieve with inorganics because usually you have some interdiffusion at the interfaces. And this is important because once we make mirrors, so here we had 11.5 bilayers. So that means 23 layers solution process. So this is the gray curve. And we compare it with a more standard conventional sputtered mirror in gray. You see we get essentially the same performance with essentially the same number of layers. So we knew we can actually really get good photonic structures. So how can we use that now? If we use now a polymer solar cell, again, why would we have a polymer solar cell? The reason is they're semi-transparent, as I mentioned before. So this is a picture from my collaborator at KAUST in Saudi Arabia. This is the solar cell. You see how easily you can look through the solar cell. So this is really coming from here, from the glass, through the active layer, through the second electrode. What I have to say is while organics, especially like polymer solar cells, have the advantage that you chemically could tune the color just by changing them structurally, often this is not done. And the reason is every chemical change you make to the polymer or the organic small molecule you use in this layer will affect performance. So we thought, well, let's just put one of our mirrors in the back. And this is now shown here. So this is this cell. We put the mirror in the back and you have this beautiful red structure. So clearly from a design point of view for architects, that's very interesting because contrary to what I show here, I just was not very good in my schematic. This mirror is essentially of the same thickness, a bit thicker than actually the active layer. So important is though also we can really change the color of those mirrors. So we can manipulate the Bragg wavelengths. That means that's the wavelengths that is predominantly reflected. And we can do that, as mentioned before, just by changing actually the thickness of those layers in your stack. And if you have thinner or thicker layers, we reflect green or red, and that's shown here. And you see this was still work from Imperial College because this is the reflection of the Imperial College tower onto our mirrors. And you also see already the size of those mirrors. They're pretty big. So we can really scale that up relatively easy because we do coat them with standard technologies. So why is that important? As mentioned, aesthetic. We can make red solar cells, green solar cells, blue solar cells without really touching actually the active material. But also from a performance standpoint of view, it helps. So if you look at the transmission of this solar cell, so this black line is actually this structure. So it tells you the active layer in particular absorbs in the 400 to 700 regime. So you have a low transmission here, and then actually you have a high transmission. So if you now make different mirrors, and especially like this one, you shine light, the solar cell has absorbs, but it doesn't absorb everything. So some light goes into the mirror and is reflected. That's shown here. So this light gets shot back into the active layer, and that's good. So you can actually harvest more light than when you have the solar cell without a mirror. And when you look now at a normal solar cell, device performance, so there you plot current density versus bias. One critical parameter is how much current you get at zero bias. So here you see the normal solar cell, and then we have the mirrors on there. It seems like a small increase in current that you get by shooting light back, but you see, if you look at the device performance, so this is the change in the photo conversion efficiency. Adding the mirror increases the efficiency by 10%. And when you remember, these mirrors were actually not even some of the best. So we definitely can actually produce mirrors with more layers that shoot back more light. Why is that important? A single device, it helps with efficiency, but if you really now want to integrate those devices somewhere, for instance, in a greenhouse, you can play with that. So in a greenhouse, you have to make sure that you have relatively high transmission. Here, the black, that's again the solar cell, where the chlorophyll absorbs. So here on the top, you see the absorbance of chlorophyll. It's around 400 and 650. Why chlorophyll? This is one of the key ingredients, the key chromophores in plants that absorb light. Then we make the solar cell, as mentioned in black, just a solar cell without mirror, relatively high transmission where the chlorophyll absorbs. Then we add mirrors in blue and red, which are also relatively open where the chlorophyll absorbs, but they shoot back light that the chlorophyll don't need. And by now, you know how solar cells work. Again, current density versus voltage. And you see here we have now a pretty big increase in the short circuit current. So the current at 0 voltage, just because we added mirrors. And I also have to say, we worked here with NC State, so North Carolina State University, with plant biologists. Having the solar cells on there did not affect the plant grow. So the hypothesis that as long as we let light through where we need it, but we harvest light that the plants don't need, we can get to good device performances. So we can integrate them in greenhouses. We can get some electricity just by the sun that also the plant need, but we just make sure which part of the light they get. So that can help for greenhouses in the desert where you need cooling, but obviously also for greenhouses in Sweden where it is cold. And of course, we can do more, especially when you think of greenhouses, buildings, solar cells. And this is to make transparent mirror. And here I mean transparent mirror for light that is in the visible wavelength regime, which you need for solar cells, but also building, but mirrors that do then reflect in the infrared, so the heat. Beside buildings and greenhouses, this is important for solar cells. So one big problem of commercial solar cells like silicon solar cell is when they heat up, which they do because they have to be in the sun, they actually lose performance. So what people did at Arizona State University with these commercial solar cells, they put a heat mirror on top of the solar cell, so shooting the infrared back to a thermal receiver, which they can use for solar thermal power, while letting the visible light through, so you could run the solar cell to create electricity from the visible light. So in our case, we can easily do that and get actually coatable infrared mirrors. And what do we have to do? We can get there by simply again increasing the thickness of each individual layer in our stack. And this was our very first infrared mirror. That's possibly now 10 years ago. So here you see nicely, we have very high transmission here in the visible, but we do reflect in the near infrared. You also see that the quality of the mirrors are very good. How can you see that? So you always see my graphs, the solid line. These are the experiments. Then you have the dotted line. You can actually simulate those mirrors with a methodology called transfer matrix methodology. So the fact that our mirrors can be so well modeled means we really have high quality mirrors. And again, you see when you put them, again, the Imperial College Tower, you see they're transparent in the visible. You don't even see here that there is something, but we do reflect the infrared. So we can make plastic infrared mirrors, so plastic heat mirrors. The problem for many applications is the reflection band, so the wavelength regime where you have the reflection is relatively narrow. And let's say for solar cells, but also buildings, etc., you possibly want to reflect all of the infrared or near infrared at least. And this can be done by changing the stacking a bit. A good example is this beetle here. Obviously, this beetle is not made out of gold. Otherwise, I think it would be decimated because people would get this gold. It has similar photonic structures like we just showed, so the DBRs, so multi-layer stacks. But what changes is rather than having all the layers of the same thickness, you start to put defects in there. We focused on what physicists call chirped stack, meaning every single layer is a bit thicker. And that's shown here. So my student at Imperial College, Stéphane Bachelivier, did an amazing job. So every single layer, in red, the low refractive index layer, in blue, the high refractive index layer, every single layer was actually 2 nanometers thicker than the previous one. And when you do that, you get actually something, a plastic that in the visible looks like silver. So here you have the reflectance, and just out of plastics, you get something that really behaves like a silver layer. And this is also shown here. If you get more and more layers, you see it in the absorption. So this is just looked through the film. Eventually, you can't look through it again. It's black. But if you look at the reflection, first it's blue, like the mirrors I showed at the beginning. But more and more, it actually becomes silvery. Having these defects also helps, which is important for solar cells. Most of these stacks that I showed before, they usually work very well when you look perpendicular to the mirror, but the performance changes when you look at an angle. I should use this schematic. When you do the chirping, you see we get very high reflection across a broad range of angles. And even at like 35°, you still have a considerable reflection. So independent how your solar cell or a window looks like, you reflect the light. And in particular, you reflect the infrared. So that means heat. And that's now just a measurement where you see independent of angle, unless you really go pretty flat to the surface, the light comes, you have high reflection. So how can we use such broadband infrared mirrors beyond solar cell? Well, one is really in building integration, and you possibly, I'm not sure if you see that, where you really want to prevent heat coming into the house. And this is really in the infrared regime. So highlighted here in red. And once the bar goes away, you see the wavelengths. So it's around 1 micron and above. Clearly, um, good windows that reflect infrared exist. They're called low E glass. They're often expensive, but what you see is they're very good in reflecting light that comes from 5, 10 microns and more. If we would use a simple mirror that we showed at the beginning, the DBR with the same thicknesses, we could already get quite a bit of the near infrared reflected. But you see, we would still have here a lot of the near to mid infrared that is there. So when we chirp now the mirror, in principle, we should be able to reflect all because we broaden the reflection band of this blue dotted line. And this shown here. So we have here a chirp DBR in blue. That's a measurement. Just the DBR by itself. The E-glass here in red, you see it starts to really reflecting above 2 micrometers. Now, when we put them on top of each other, you see we can get actually really the performance of the DBR in blue, and we can get the reflection of the E-glass. So we really get a good combination where only like the 1.5 micron area has a dip. And again, you keep the transparency, contrary to a lot of the e-glasses that are used nowadays. So we really could show that we can get to a broad near infrared reflection, and importantly, with a small angle dependence. So independence, how the light comes in, the reflection works. So what I haven't talked about so far is how do we get these polymers with a high refractive index? Because we always needed in every single layer a low refractive index layer and a high refractive index layer. And as mentioned before, we have a very simple system. So it's made out of polyvinyl alcohol, so like polyethylene, but with this hydroxyl group there. And we put them in solution with titanium dioxide precursor like titanium tetrachloride. You can also use titanium isopropoxide, etc. And what happens, these two react with each other. It's a polycondensation. So you split off HCl in the case of titanium tetrachloride, or alcohols if you have titanium isopropoxide, and you start to form this inorganic polymer, titanium oxygen titania, and actually reaction to titanium dioxide is prevented because the precursor reacts with the hydroxyl group of the polymer. So you get actually an amorphous material of inorganic macromolecules that are stabilized by these carbon chains, so the polyvinyl alcohol. And for this talk, not that important, we think usually that titania, and that's why polyvinyl alcohol is so good, reacts and forms this bidentate forms these bidentate structures, meaning that titania grabs two hydroxyls that are next to each other, and therefore PVA is so good. So when you create this hybrid, you get a very nice transparent film. Because it's amorphous, you prevent crystallization of the PVA. And that's very different than if you would take titanium dioxide particles, because then you would have high refractive index particles, low refractive index polymer matrix that leads to scattering, as you see here. That's why we use titanium dioxide in white painting. Clearly, we needed to know about the refractive index. We want to have a high refractive index material. For this, we did ellipsometry, and not surprisingly, the higher the amount of your titanium oxide hydrates polymer, the higher the refractive index. And it's actually very homogeneous material, telling us we don't have nanocomposite, but really this molecular hybrid. Why? Independent, where we take the different refractive indices and plot it against volume content of the inorganic species, we have a very nice linear relationship. So the titania polymer are really very homogeneous. It's one structure, one material. For photonic application, what is nice, we can really push the refractive index when we anneal. Again, it's a polycondensation. It's a condensation process. So when we are able to get the condensate away, we can get to higher refractive indices. So we really have a highly tunable system where we go from a refractive index of 1.55 here in blue, the neat polymeryl alcohol, to close of a refractive index of 2.01. So usually it's like 2 maximum. What is also important for many applications is that we have no loss, meaning there should be no absorption, no scattering. We measure that very simply when we measure the transmission and the reflection. In black is just the polymer alcohol. In red is the hybrid with 20 volume% titanium oxide hydrates and 80% oxide hydrates. And what is key is you have here this dimple, so you have a lower transmission. This is not absorption, this is not scattering. Why? Wherever you have a low transmission, you have a high reflection. So this just tells you actually the deeper those oscillations are, the higher the refractive index. These are not losses. And they're really easy to synthesize. I saw some of my students are here and they have used them. And what is fun now, we can really do very fundamental physics with very sensitive materials. And I use maybe my last 3-4 minutes, so there's still time for questions. We make DBR microcavities. What does that mean? So we looked at the mirrors already, and here you see nicely that at these interfaces, parts of the light is reflected, parts is transmitted. You saw that we therefore get wavelengths that are reflected. So we have a stop band like Campi here. So these were the mirrors. Now, in case we use DBRs on both sides of a structure, so we have two mirrors and in the middle we have a medium, we can get descending waves. And because we have two DBRs and this gray part here or here, they act as defects. You see in the transmission, rather than having a whole regime where it reflects, you open up a little high transmission state. So this is called the optical mode. So you get actually a mirror, but the mirror lets a very thin part of the light getting through. So we prepared these mirrors. Again, it's the hybrid. I will not go in there. We had relatively few layers for the mirrors, so these were not perfect mirrors as I showed before. But you see that now, again, in solid line is the measurement. When we have this structure with this spacer layer, this defect layer in there, we don't have a mirror, but we have a mirror where at very specific energies or wavelengths opens up. And again, we have a pretty good agreement with theory. So these are the dotted lines. So why would that be interesting? Well, you can put an active material in there, something that emits light, like a conjugated polymer. And then you have excitons that you trap in this cavity. So that's why they're called microcavities. What happens when you do that? So you have you shine light into your pink layer. You create an exciton, which is a whole electron pair. And in case you design them correctly, the physicist will call it a near resonant condition. This light that is sort of trapped between these mirrors and the excitons, they couple together, and you get what the physicist will call light matter coupling. What does that mean? In case you only have the exciton, if you would look at the emission or reflection, it will be independent on what angle. So that's the K2 or angle that you see there. You have it. It's always the same emission, reflection, etc. If you only would have the cavity, we saw you have an angle dependence. That's the pink one. Now, if these two couple, you see actually we get two different features, an upper polariton branch and lower polariton branch. So they combine some features of the optical mode, so these ones, but then get to the exciton one. And we did this, so we used a parallel derivative detail. So it has a very nice photoluminescence. we took the cavity mode where we have the highest photoluminescence. And what now you see here, this is a measurement. It's a reflection at different angles. So we measured the reflection at different angles. And you see here one branch, and up here, hopefully, you see another branch. So, and if you look at theory, you see it a bit better. You see how the exciton in pink and the optical mode, the dotted line in blue, they merge and they create this upper polariton branch and the lower polariton branch. And this is just another example to show this is very reproducible. Why is that so important? You can now really start to do deep physics, how light interact with matter, and especially matter like polymers that are disordered. And because we can fine tune our materials so well, it's very easy actually to get them onto complex structures, sensitive materials, etc. Finally, of course, we not only want to get light interacting with matter, we also want to guide light, and we want to guide light around the corners. And this was when I just finished my PhD in 2001. One paper came out that showed that you using photonic structures, so low refractive index holes, high refractive index like gray silicon, you can bend light around the corner. So in our structures, we can do that too. So by simple lithography and hopefully eventually melting, we can make these holes in our hybrid polymer. So we have a low refractive index holes, hybrid polymer. And just to show, we can make little pillars. That was obviously an animation and they're not as soft as in that movie. So with that, I should stop. I see I get to the end of my talk and I definitely want to leave time for questions. There are options also on plastics and to use plastics in a good way to, for instance, reduce electricity use and carbon emissions of buildings. We can help efficiency of solar cells by using infrared mirrors that reflect heat, but also anti-reflection coatings to ensure more light gets into the solar cell, so that eventually we can have solar cells not only in countries and cities with a lot of light, but also in countries and cities where there's actually not much light. But we also can go really further and look into very fundamental physics applications when we have two mirrors. And I hope you see that here slightly red, light emitting like a semiconductor, where suddenly we have light interacting with matter. And all of this is because of a hybrid. And I have to say, this was an accident that we produced this hybrid. We wanted to work with the fashion industry in London and get photochromic systems done. And that's by chance we created, rather than nanoparticles, polymers. The key was, though, we figured it out that we actually didn't get what we first wanted to do, but this polymer, this molecular hybrid has opened up so many opportunities. It is actually really fun. And with that now, I really want to thank my students, both at Imperial College and Georgia Tech, collaborators, funding still from the European side as well as in the US side. And just the last announcement, since June, I'm associate editor of Checks, and hopefully we also will get papers from Africa. And with that, I end my talk just with this picture with Super Mario actually being static. And I hope there's still some time for question.
Thank you so much, Natalie, for this nice talk. Very informative. I've actually learned quite a lot from it. And I believe we have quite a number of questions from the participants.
Okie doke.
Yeah, and I note that you've talked over different areas in material science, from how the polymers can be used in photovoltaics, can be used in solar thermal, can be used to allow specific wavelengths to pass through them, and how you can bend light with them. There are quite a lot. So I'm just curious. Let me go first with the questions.
Yeah, thank you.
I believe you work more with organic solar cells.
Yes, I do.
But have you ever tried them out with maybe other types, perovskites, to see how they'll behave? I know we are moving green, but can it improve the efficiency of silicon solar cells?
Well, if you stack them, you get there. And again, it's not only about the efficiency. I think the key thing for the organic solar cell is really that they're semi-transparent, as this picture here showed. So you can integrate them in greenhouses, and the plants still grow. This would be impossible with silicon solar cells. So I would not say polymer solar cell or metal halide perovskites compete with silicon, because efficiency is maybe not fully there, but it's not only about efficiency either. So a good example for polymer or solar cell is the integration in greenhouses. The other one is also weight. So during COVID, for instance, one researcher in Australia, he printed organic solar cells and he drove through whole Australia because he could roll up the solar cells. He drove, charged them, drove the next day again. Impossible to do with silicon solar cells because just the weight would be far too difficult to carry the solar cell around, even when you have a big truck. So I think what really the point is here, what are the applications where you can't use the existing solar cells? So building integration, integration in cars, where do you need the lightweight? Where do you need the semi-transparency?
Thank you. And for the fluorinated polymers, the mirrors made from fluorinated polymers, how long do they take to degrade? Do they really degrade?
We haven't specifically looked at the fluorinated polymers. Let me go and see the structure. I think it comes, yeah, it doesn't matter. But if you simply look at one of the mirrors, here there is. It's also okay to, so here's the fluorinated. This is a commercial material that we can buy. I have to say we had not looked at the degradation of the polymer. I think the key is, I think you produce a lot of small molecular fluorinated materials upon synthesis of the material. So before you have the polymer. What I can say is we used these type of anti-reflection coatings as well as the mirrors that come in the next slides here. And these were the big mirrors, as I showed with the Imperial College Tower reflection. We put them into the Saudi desert. So these were multi-layer structures. I don't know anymore how many periods they had, so how many layers. But the mirror survived 3 months in the desert without degradation. So there was no yellowing, etc. Clearly, did the fluorinated polymer lose some of their fluorines? I have no clue, though I would have assumed you would get yellowing eventually because you create a double bond at the backbone. So in short, we don't have anything quantitatively, but qualitatively, it seems at least the stack is pretty stable. And also when you look at the polyalcohol polymer, people would actually usually possibly more worry about the polymer, the hybrid rather, I'm not too far, than the fluorinated polymer. Also, the polyvinyl alcohol is actually the hybrid material with polyvinyl alcohol is very stable. Usually, polyvinyl alcohol would definitely degrade in a Saudi desert. The reason is usually this hydroxyl or hydroxyls are attacked, and therefore you get then here double bonds again, leading to yellowishing. But in our hybrid, we actually consume a lot of the alcohols, so they will be very difficult to actually get to. And therefore, we know the hybrid is definitely far more stable than the polyvinyl alcohol by itself.
Thank you. That is good progress. Now, another question that I have is for the infrared reflection. How deep have you managed to go in terms of reflecting the infrared light? Up to what wavelength have you managed to go?
When you saw with the chirped mirror, to be honest, I can show actually the very first infrared mirror and not the chirped one. So this was the first one, which was not broad reflection. So how can we shift it to the infrared? As mentioned, we can make thicker layers. So if we make the red and the blue layers thicker, this band here will shift to the infrared. So in principle, we simply can go make thicker layers, getting to 1 micron thick. This one I think was 150 nanometers for the hybrid layer. So you can go easily to 300 nanometers. You shift this. Where you have to be a bit careful is what you see here in the dotted line, the calculation, which is hidden here in the measurement, the solid line. Eventually, similar like in X-ray diffraction or optics, this is the first order reflection. This is the second order reflection. So what you have to be careful is if you shift this one too much over here, eventually you will shift this second order, this very sharp peak over here, into the visible. But again, this changes a bit once you go to these chirped mirrors, because the chirping, because you have defects, you can again think of X-ray diffraction. It broadens the width. That's what we want. So we want to broaden the reflectance. Also, in many cases, it prevents the second order to be there. Again, like with X-ray, the better order, the more higher order reflections you see. The less order, the more defects you have. You start to lose the second order reflections, and therefore then we can get from 800 to 1400. In case we would add more layers, we could push it further over here, or if we simply start, let's say at 900 and to thicker layers, we push this one to like 1600, 1800. The beauty is we can design it. If you tell me you want to have the reflection at 2 microns, we can design the mirror so it reflects at 2 microns.
Thank you. My last question, just a quick one. I'm just curious whether you have any patent from this work or some startup from this work. Maybe you can tell us.
No, we have not. The reason is I think we were A, busy with the science, B, the material is actually very difficult to patent because there are, of course, a lot of composites of titanium dioxide and polymers to increase refractive index. And therefore, we would have needed to make it very specific. And then, well, it would have been a narrow patent really highlighting its titanium oxide hydrates. But even that would have risked to infringe with titanium dioxide patents because, of course, patent lawyers were clever. They never really spell out titanium dioxide, but often use titanium OX and other versions there. So the material per se is difficult to patent, and everybody who knows about patent, the thing is, how would you be able to check that somebody infringes? So, I mean, a patent is only worth something, in my opinion, when you can prevent people doing something, but companies possibly could do this hybrid, and it would be very difficult to show that this is this specific hybrid formulation. So we decided just to focus on the science and put the structures out there.
Yes, I agree with you. Some patents are quite vague so that you cannot argue your point. And thanks for that. I note that you have a question from, is it Jan or is it Jan? Please
Hi,
go ahead.
it's Jean-Luc here from Chicago. Hey, Natalie, very nice talk. I have a question regarding your IR reflector. Have you thought about like having like up converting material in the mirror or in the reflector layers so you can actually up convert the infrared photon into the spectral region where your
For the solar cell.
Exactly. So
Yes.
and so you can drastically boost the efficiency of the solar cell if you can take advantage of up converting process or technology.
Yes, we have thought about it. We actually have not done it yet, simply because of man-woman power. But actually, for the audience, so what I showed so far is a solar cell, and we put just a mirror on top to reflect the um, light that the solar cell needs, but was not observed in the first round, like for the greenhouse solar cells. But what Jean-Luc now mentioned, and I think it's a super nice idea. We thought about it. And yeah, maybe somebody else does it or we do it. It's to put into the mirror. And actually, it's a very good point, Jean-Luc, because what is nice, because we solution process, we can integrate dyes into the hybrid, or we could put it into a PMMA as a low refractive index layer. So we can integrate other species into our mirrors, like something emitting, or like what Jean-Luc mentioned, something that upconverts, which means we could have a solar cell. I show here my phone. Maybe no, it doesn't pick it up. Then light comes here. We shoot the light back because it's a mirror, but in the mirror, we could also integrate a species that absorbs infrared, which will be up, and then down up converts, which means up converts in energy, higher energy. In wavelengths, it means lower energy. So you can actually harvest additional light that usually the solar cell would not absorb. And yes, beautiful idea. And either we do it or somebody else does it.
Somebody else will do it. Yeah. Yeah,
Yes.
we've been working on some up conversion material here, but mainly organic. We haven't tried to up convert near infrared photon yet, but we've been doing up conversion of red photon into blue and UV photon.
Okay,
Nice
nice.
talking.
Yeah.
Thanks.
Thank you, Jean-Luc.
Thank you. Anyone else with a question, comment? Any participant?
I can see in the chat there's some comments there.
Oh, okay. Okay, let me check. So there's a comment from Abebo. Let me try to rephrase the question. How do you perceive multiple exciton generation affecting the solar cell? I presume that's the question.
As you saw, I'm not fully understand what you precisely mean, but if you think we get excitons, then indeed some of the light gets through the cell, comes back. It's not really that in the solar cell we have the exciton interactions. That would be more really going into the microcavity, where you then really have to design your structures much more carefully. In the solar cell, it's simply you get more light back. And therefore, the solar cell, you have higher short circuit current, but nothing else is affected. So your open circuit voltage, for instance, stays the same. So you really see what you do is you increase the amount of light that gets in, but and therefore you have higher short circuit currents, but that's all. So we don't see other effects. And if you think of exciton interactions or whatever, I think that would really then much more go into the microcavity regime. But I'm not a physicist, so we see in the solar cell what we expected to see.
I've just unmuted Bebo if he wants to talk.
Pardon?
I said I've just unmuted Bebo if he can talk. Yeah, I don't know if he's still there.
Yeah.
Okay, so I think that is sufficient. Anyone else with a question before we close?
I think I'm sorry. I have a follow-up question regarding the exciton generation and integration with the solar cell. Have have you looked into generating multiple excitons in the active layer, and how the solar reflector affected the photophysical process? Like, say, for example, you have like an organic light harvesting system that can generate multiple exciton, like say through singular fission. And if you have work on something like that, and how is the photophysical process, like, pay off, or the outcome of the process if you have the solar reflector?
Okay, that's a good question. And actually, now I think I understand what Abebe wanted. So you have completely different active layer, but actually we have not looked into this. So, but it's interesting. But yeah, in short, we have not looked into other, like we really used always the conventional donor acceptor blends, but not with other
Okay.
photophysical properties.
Okay.
We
All
have
right.
done OLEDs where then you see other effects, but yeah, on the solar cell side, we haven't. Yeah.
Okay. Thank you so much. Thank you.
Okay, I can see Professor Mulolo has a question, but before I allow Professor Mulolo, because I also want to request him to close our meeting today. Is there anyone else? Okay, so Professor Mulolo will ask the question, and I wish to introduce Professor Mulolo. He is the Vice President, MRS. Thank you, Professor Mulolo. Go ahead.
Okay. Thank you very much, Natalie. Thank you for giving us such interesting talk. I want to ask a few questions. Can you hear me well? Can you hear me well?
Yes,
Can
I
you
hear
hear me
you well. Yes, we hear you very well. So now you just froze. I did hear
When
you
you
very
create these
well.
structures, how do you characterize?
Good question.
When you- Yeah, how do you characterize the structures?
So I mean, you saw the SEM pictures, so they simply show that we don't have interdiffusion. We also can make an element map, so we see titanium is not diffusing into the low refractive index. For all the rest, we usually look at the structures really optically because this is nearly the most sensitive one with respect to checking on the interfaces. So I showed you quite a few characteristics where we show just the stop end, so the transmission, the measured one, compared it with the transfer matrix method. And usually we have like close to 100% agreement that tells us our interfaces are good. The thicknesses of the layers have to be what we wanted them to be, because otherwise the calculation would immediately deviate from our final structure. So it's indirect,
Thank you.
but yeah.
I want to ask you a question.
Yeah.
Thank you. Yeah, I want to ask you a question about reproducibility of your results. If you give me the recipes and I do it, would I get the nice you will get the first time, or how to do many things? In particular, if somebody wants to get transmission or absorption at a particular wavelength, is it possible? Or you just have to try and
Yeah. In short, in principle, it's very easy to reproduce because it's simple dip coating. We are happy to share the recipe. There are groups who made the microcavities with our hybrid, and they got very nice microcavities. The more complex answer is, though, as with cooking or other things, you need a bit what we as Swiss Germans say, Fingerspitzengefühl. So you have to really look at the material with dip coating. One has to be very diligent. So we do for every new solution usually a master curve because, you make a solution of the hybrid one day and then another, even when you use the same material, room, the humidity, etc., changes things a bit. So we make a master curve of withdrawal speed and what thickness we get with that solution. And with that, then we know how fast we should go to get to a certain thickness. So in principle, it's very easy, though the devil lies really in the detail. One has to be very careful. One has to be very tedious, establish these master curves. And also, we learned it a bit the hard way, try to circumvent, we use a fume hood, but try to minimize airflow, things like that. But if you have the recipe, you dip coat, you will get a DBR. The first one, the second one, the third one will possibly not be the best DBRs yet, you know. But it's
Yeah.
practice.
Thank you.
It's really like cooking.
Okay, yeah. Thank you very much. Yeah. So once again, let's thank Professor Natalie for coming, for giving us this seminar. So we're very grateful to you. I want to make a few announcements and then we'll close. So every month, the last Thursday of the month, typically, we have these seminars. So it would be good if we could tell our friends and have them join us also. If you have ideas on some people that we should invite to give the talk, you can let us know also. We'll like to have many people join the talks and give this important seminars. Yeah. And I think there'll be a recording because we are recording it. So it will be possible to watch the recording if you want to watch it again. And then the other thing I will say is apart from our meeting every month for this seminar, there's a big meeting coming up, as many of you know, in December 2026. So we look forward to having Professor Natalie and other people, Jean-Luc and other people, including everybody that's online now. We look forward to having you in Kenya. Apart from the conference, you can come for the safari also. It's great and fantastic. I've done it once. I've gone to the for the safari once in Kenya and it was very good. So I will recommend that everybody plans to attend the conference in December. Okay. So again, we thank Professor Natalie and I thank everybody for attending this seminar. Thank you very much, everybody.
Thanks for giving me the opportunity. It was a pleasure and I definitely look forward to Kenya.
Thank you.
Thank you. Thank you, Natalie. Thank you, everyone.
Thank
Have
you.
a good evening. Have a good day.
Yeah. Bye, everybody. Thank you.
Thank you, Natalie.
Bye, Samuel. Thank you.
Bye.
It was lovely.
Oh,
Bye.
Bye.